All right, there we go. Now I'm getting tone. Thank you for pointing that out. Sorry about that. But anyway, we were just recapping what we were doing last time. I'm just making sure that it works. And it still doesn't work? Oh, there we go. Yep. All right, good. I should have done that in the beginning. Sorry about that. Anyway, we were just recapping what we were doing last time. And again, the recursive functions have the same three aspects as a loop. An initialization, a continuation, or termination condition. And then you have to make progress towards that termination condition. We also briefly talked about good and bad. I'm of the perspective that recursion probably is, all things considered, the bad, a bad strategy to follow. But yeah, let's go ahead and put on our devil's advocate hat here and look at it as a good tool. Lots of divide and conquer style algorithms initially use recursion to present a solution to the problem. Right? For example, we're going to see this when we start doing searching and sorting. If you want to, sort an array, split it into two parts, and then sort this one and sort this one, right? And then you can merge them together. Or quicksort is another divide and conquer strategy. Binary search is another divide and conquer strategy. And so it's very natural to use recursion for those kind of divide and conquer solutions. Lots of functional programming languages force you to use recursion, like Haskell or Scheme or Lisp or something like that, or they highly prefer you to use recursion because it's a completely different style of an approach to programming languages. And of course, recursion can be clean or beautiful or easily understood. If you look back at the definition here, the mathematical definition of the Fibonacci sequence, and you look at our function right here, it is almost virtually a one-to-one map there, right? And so if you are really into that mathematical way of thinking of applying functions and composing functions, all that stuff, then it's right down your alley. Most people don't think like that, though, right? The thing to take away here is that somebody's clean or beautiful code or easily understood code is somebody else's confusing and dirty and ugly code, right? These are all kind of subjective things. Whereas the bad parts of recursion are objective. It can be extremely inefficient. You can risk stack overflow with a deep recursion because you are making function call, function call, function call, function call. Now there are ways to mitigate these risks, and one of the ways that I'm going to show you today in both C and Java. Okay. Looks like we are back. Yep, good. Thank you for the call out there, on YouTube here. Right. So let's talk about eliminating recursion. Right. In general, actually, recursion is not necessary. There are programming languages that don't even support this. Early versions of like Fortran or COBOL or something like that don't support it. You can always take any recursive function, like we did with the Fibonacci sequence, and transform it into an iterative solution. Right? You can come up with an iterative solution. Or you could use a data structure. Instead of abusing that call stack to do all your work for you, you can go ahead and create an in-memory stack and push things on top, pop things off the top, and you don't have to risk the recursion, risk the stack overflow. You can have a much larger stack that's allocated on the heap. Right? You can always simulate it using an in-memory stack. Okay? You can, in general, take any recursive function and rewrite it to an equivalent non-recursive solution. Right? Now, I'm saying in general here because there are recursive functions, mathematical functions, that are not computable. And you can't unroll them into an iterative solution because there is no iterative solution either. Right? So that goes way beyond the scope of this course. Don't worry about it. What the solution that there's another solution called tail recursion. The compiler can optimize away all your function calls. For example, if you're only putting in parameters, right? Like the countdown, remember the countdown? The only thing that was stored in each one of those stack frames was the count, right? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. At which point then we started popping those all off the top, right? You could transform that into a tail recursion. In fact, compilers probably do, and say, you don't need these stack frames anymore, right? I'm going to go ahead and just I'm going to change your code into either a non-recursive version or something where you're not making function call, function call, function call. You're reusing this stack frame over and over and over again. Right? In other words, you're using a variable, int I, right, instead. Okay. What I'm going to show you, though, is memoization. Right? That is not memorization. It is spelled correctly here, trust me. Yes, it is a made-up word. All words are made up, right? So it's not memorization, but it's memoization, right? So remember that big giant diagram that I showed you of the Fibonacci sequence being computed? And then we realized, well, wait a second, we're recomputing Fibonacci of 5 3 or 4 times, right? Don't do that. If you need to make a computation, pay for the recursion, right? You're just going to have to pay for it, right? But store it or cache it, so that if you need it again, you reuse it, right? So this is what a cache is. It's a storage location. Once you've computed Fibonacci of 5, never compute it again. Just store it off over here in this cache, and you check the cache. And have I already computed Fibonacci of 5? Yes, here's the answer right here. Okay, I'll use that. I'm not going to make a recursive call. I'm just going to simply use what's in the cache, right? So when you need a value, you first check the cache, right? If it has been computed, use it. Otherwise, again, pay for the recursion. Clean up my spelling here. There we go. I think that's everything. So this is a cool idea, right? It's kind of the best of both worlds. Fine, you really want to use recursion, we'll go ahead and use recursion. But we're not going to do the same recursion over and over and over again. We are going to save those answers and look them up in the cache the next time you need them. Right? So we're avoiding all of the recomputation. We are taking that big giant tree that we drew and we are pruning it out, right? So that it is now not a big giant exponentially sized tree. Now it's just a nice stick, right? And that's much more manageable. That is going to be far more performant, okay? Let me show you how to do it in C first of all, because you're going to be doing this next week in your hack. So a cache is just a storage medium, right? You put stuff in there so that you can look it up and take it out later. In C, what could we use as a cache? An array, right? So let's do that. I'm going to go ahead and cut and paste this function right here and use it as a model. Of course, I can't call it Fibonacci because I can't have two functions with the same name. So I'll call it Fibonacci memoization. It is going to be a recursive function. If you have not computed the value of the nth Fibonacci number yet, then we will pay for the recursion and make a recursive call to Fibonacci of n-1 and Fibonacci of n-2, but this version instead, okay? So I need to check the cache first. Instead of looking at my base conditions here, let's go ahead and check a cache. If the cache has the value for Fibonacci of n, then use it, ... Else, go ahead and pay for the recursion. Now, obviously, this is not real code here, right? So let me go ahead and put that into a comment instead, right? And I need a cache, first of all. So you said that let's go ahead and use an array. All right. And I'm going to call it a cache. What kind of value should we hold in this array? We could do integers, right? But yeah, we want longs here because we want big Fibonacci numbers, right? So long cache. That is my array. How big is that array? I don't know. That's your problem, right? I'm just simply going to look in this cache here and see, is the nth value already pre-computed for me, okay? All right, so if the cache of n is valid, how should we do that? Well, remember the Fibonacci sequence itself goes from 1, 1, 2, 3, 5, 8, dot, 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 dot. What is a value that will never appear in the Fibonacci sequence here? 0. So if it's not equal to 0, we can safely say that it has been pre-computed. Let's go ahead and use it. Return cache of n. Otherwise, it is equal to 0. Otherwise, it is 0, has not been computed. And so we'll go ahead and compute it here. But what do we need to do? Once you compute this value, should I just blindly return it? My cache will never fill up with stuff then. So let's not do that. Let's go ahead and create a long A for the first one. Create a long B for the second one. And then a result here, long result, is going to be equal to A plus B. And then I will eventually return that result, of course. But before I return it, what should I do with it? Store it, cache it. Cache of n is equal to result. Okay? Now, there is still a problem here. What did I eliminate? The base conditions. So remind me that we need to take care of that. But let's go ahead and use Fibonacci of memoization here. Right? So I'm going to have to pass in the cache. Right? I need to set that up. So remember that a loop has 3 parts: an initialization, continuation, and making progress towards that continuation. My initialization here has changed. Not only do I have an input, I want the 23rd Fibonacci number. And remember that this is -1 here because we were off by 1. Wolfram alpha likes to start at n1, right? And so just to match these numbers here, I'm subtracting off 1. Okay? But otherwise, I've got the input n. And I now need to initialize my cache as well. How big of an array do I want? Well, first of all, I should typecast it. How big of an array do you want? 23 minus 1. All right. So that's stored in n, right? And size of integers? Longs, good. Times n. Now be careful here. Remember, our definition starts at, I guess it does start at 0. Right? So we're good, I think. Yeah. All right, n. And why is this okay? Generally, if I did the Wolfram alpha way, I would have to start at 1. And so I would burn the 0th element and then go all the way up to n plus 1, or the index n. And so I would need an array of size n plus 1. All right, let's go ahead and see if this compiles at least, or if I screwed up something up here. Fibonacci declared here, Fibonacci memoization, too few arguments. Really? There's a long cache, there's int n. Too few, yeah, there we go. I forgot a semicolon somewhere. There we go. There we go. Get rid of all this. Still some problems. Oh, there we go. So yeah, you're right. I need to put in the cache on the recursive calls, right? And pass that forward. There we go. And now it runs. All right, so Fibonacci of 23, of course, according to Wolfram alpha here, adjusting for the off by 1 error here, 28,657. So, segmentation fault, right? Why? What were you supposed to remind me about? Base cases. Did we take care of base cases up here? Nope. Where should we take care of base cases? If you could take care of them in the function, by the way. You could have base cases and then you put those into the cache. Or just take care of that up front. Cache of 0 is going to be equal to 1 and cache in my array, right? Apparently the default for this compiler, for this system, is to 0 everything out. Is that always the case with malloc? Nope. So what we're going to do is we're going to fill it up with those values now. For int I equals 0, I is less than n, I plus plus. Right? I will assign to cache of I the value 0 as a flag value. 0 indicates the value has not yet been set or computed. You could set it equal to -1, right? And then you'd come up here and set, as long as it's not equal to -1, then that means that it has been computed. You just need some value, some flag value that says this has not been computed yet. Right? And I chose 0 here. Okay? Now, this is much safer, but of course it'll probably be the same results. All right, let's go ahead and try to find out what the, 60th number is. Now remember, with the original naive implementation of a recursive version here, how long would this take? Years, right? Thousands of years, right? Even if I'm generous with the computer that I gave you to do that, right? Let's go ahead and find out. Oh, okay. I don't know if that's correct or not. Did I recompile? I didn't save. There we go. That's way too. Oh, what? That's not the 60th number. I think that this is going to be overflow. So 50th. That is certainly. That's 12 billion. That'll be representable. So 50th Fibonacci number. Ah, darn it. There's something wrong here. Aww. Yeah, go ahead.
Why are we returning, if we get the flag, why are we returning that?
Because it has been, the Fibonacci of n has been computed. It is stored in the cache. Go ahead and here's your value. Right? So you've computed the Fibonacci of 8, whatever it is, and you put it in this array. And I see, oh, okay, it's already been computed. I take it out and give it back to you because you asked for it, Fibonacci of memoization. I'm calling it.
Then why do we return results in the else?
You still have to return it. You have to. I mean, it's expecting something to be returned here, and we pay. Otherwise, we pay for the recursion, right? And then we put a plus b here, and then we put that result into the cache so that it can be used later. But you still have to return the value. I still want to know what the Fibonacci of n is. Right? I screwed up somewhere, but style. Anybody see? If it's more pretty, then maybe we can see it. I don't see what's wrong here. Darn it. Oh well. 50th Fibonacci number, n, and long decimal. That should be right. Oh well. I'm not seeing it. Go ahead. Maybe I do need n plus 1 here. Why would I need n plus 1? Because I'm subtracting it before I use n plus 1. So I don't think that that's it, but whatever. Let's find out. 125862, 125862. There you go. Right. Yeah, I just need to make it one larger because you do need the nth one, right? I want the nth Fibonacci number. I confused myself because we're off by 1 here, and so ours is running from 0, 1, 2, 3, 4, 5, 6, 7 up to and including n, and so I need to make my cache as big as n. I need that nth index, meaning that I need to add 1 to accommodate for the fact that it is beginning at 0. Right? So obviously I was off by 1 there. Right? We can test it more. I think you can get up to 60. 158 or 1548, blah 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 blah. 60. Come on. All right, maybe it's doing the bad. 1548, blah, 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 blah. So I'm convinced it works now. But did it take 10,000 years to compute? Nope, it was almost instantaneous. Why? Because I took that big, giant, exponentially sized tree and I cut it down so that there was only one basic computation path in that tree. And when I did that, that made the tree into just this stick. It's no worse than the iterative version, but I've got a hybrid solution here where I am using recursion and to solve the problem, but I'm also using memoization and additional cache to cut down on all the extra work. Now with the remainder of our time, let's do the exact same thing, but let's do it in Java, and let's do it even better. Right? So let's go ahead and create, first of all, a Fibonacci function so that we can then correct it. Public static. I could return an integer, or I could return a long, because both of those are supported in both languages. But even longs have a limitation to them, right? If I go back over here to Wolfram Alpha and ask, a long is a 64-bit signed integer, so we can express up to 2 to the 63rd minus 1, that number right there, whatever that is. Quintillion, 9 quintillion something, right? Instead of the 2.147 billion. In Java, I've got an alternative. I've got this thing called big integer. Have we briefly talked about it before? It's big, right? It is an arbitrary it is an arbitrarily large number. Right? It is a GNU. I forget. Anyway, there's a term for it, but basically, it doesn't represent things with a fixed number of bits. If there's overflow and it needs more bits, it allocates more memory for you automatically under the hood. The drawback here is that you can't take a big integer and say plus this other big integer. You have to do it all in function calls, and I'll show you that here in a second. But we're going to go ahead and implement our Fibonacci by returning a big integer. Right. Oops, sorry. There we go. Now I'm going to have to import that, but it is part of the standard Java math library. Right. See, Java math big integer. Okay. So now let's go ahead and implement the normal recursive version of this just to see how big integer works. So if n is 0 or n is 1, I need to return 1. But the problem is that 1 is a regular old integer. It's not a big integer. Even though it's a small integer, I still need to use this class up here. Fortunately, they see 0 and 1 as so commonly used that they put 1 in there for you. Big integer dot 1. Right? That's the big integer representation of 1. Else, I'm going to have to pay for the recursion. So I will return Fibonacci of n minus 1 plus Fibonacci of n minus 2. There we go. But the problem there is, like I said, you can't just take this big integer and add it to another big integer. What do you have to do? You have to make function calls. So I'm going to say big integer a is equal to one call to the Fibonacci, just like we did with memoization here, and big integer b is equal to the second call to Fibonacci. And then I want to add them together. So big integer result. Ideally, again, what I would like to do is something like this. Some languages support this. This is called operator overloading, where you can make the plus sign act on different data types. For example, you could have a set and another set, and then you could add them together. And what would that be? Well, maybe a union. Maybe if they're lists, maybe you can append them together or something like that. But unfortunately, fortunately, depending on your point of view, fortunately, in my point of view, Java does not support operator overloading. It supports it in one instance. Where else have you seen the plus operator in Java, other than addition? Appending, we call that, with strings, we call that concatenation. So it does have a little bit of syntactic sugar, but it doesn't have full operator overloading. You can't do this. You have to call methods and functions a dot add b. That returns a new big integer that is a added to b, or b added to a added to b. Right? And ultimately, I want to return that result. There we go. Down here, I'll have 10, right? And I'll go ahead and say big integer result is equal to a call to Fibonacci of n, right? And printf system.out print ln. I'll just print out the result. I won't worry about the formatting here. So what was the 10th Fibonacci number? Do you remember from last time? I think it's 89 or something like that. Yep. 89. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. What would be the 11th one? 55 plus 89 is 144. I'm convinced it works, but of course, if we tried to do something like this, 1100, 100, the 100th Fibonacci number, big integer can represent this, right? Because it can represent arbitrarily large values. So 101st, right? Fibonacci. Do I have to add or subtract? I forget. That's just network lag. That's not computation lag there. There we go. Oh, what? Fibonacci number. 101st. Maybe it doesn't know what I'm talking about. There we go. There's the number. Should I be wait? It is still running, by the way, because I've got the stop button over here. Should I be waiting for this? We're back to 10,000 years or so. Stop it. Right? Let's use memoization here instead. Now, I could use a regular old array, but this is Java. We can afford nicer things. Right? So what are some nicer things that we can afford other than just plain old boring arrays? Lists, sets. Right? What am I doing here? I want to basically take 100 and map that to this value right here. Something like that. I want to map 10 to 89. I want to map 11 to 144. So what could I use instead of a plain old array? A map. Right? A hash map in this case. So let's do that. Let's do that first of all statically. Public static map. And what types am I mapping? I'm going to map an integer, 10, to a big integer. Now 89, that doesn't need to be big, but I'm going to be using big integers here. Right? And I'll just call it m for map equals new hash map. And it's able to figure out that I'm mapping integers to big integers. Right? I'm making it static up here so that it belongs to the class. Otherwise, I would have to pass it in every single time right here, just like I did in C. All right, let's modify this function so that we check the cache first here. So if m dot contains key n. So if we have computed it, then use it. Return m dot get whatever has been mapped from n. Otherwise, compute this, the sum, and then before you return, put it into your map, m dot put. N maps to result. Okay? Now, is this going to work? Let's find out. Ooh, exception. What does that look like? That looks like an infinite loop to me, but it looks like, more to the point, it looks like an infinite recursion. Right? Remember what did I ask you to remind me about over here? The base cases. What are we not doing anymore over here? The base cases. So I could do that in main. I could rewrite my function here to take care of the base cases, but I'm going to show you something cool. Right? A static block. Right? In this static block, I can put whatever code I want. m.put. And so here I'm going to take care of those base cases. 0 will map to big integer dot 1. And I also want to map 1 to big integer dot 1. Now before we see that this works, let's understand what this is doing. This is a static block with an opening curly bracket and a closing curly bracket. You can put whatever code you want in here. When the class gets loaded up by the Java virtual machine, this block will be executed, but only once when the class gets loaded up. Right? So it's a way of doing some initialization code that on static variables that you don't have to worry about it and put it into a function. Right? If you could put this into a function and then you'd have to call that function at some point, but by putting it into a static block, then I'm letting the Java virtual machine execute this code, this initialization code, when it loads up that class. Yeah?
So it's basically like putting it at the front of the beginning of main?
It's kind of that way.
Okay, but it's not
But you can do it if I didn't have a main,
oh, okay.
right? I don't want a main. Math library doesn't have a main. But maybe it has some initialization parts like setting pi or whatever. That's probably just, I mean, it's kind of like doing it like this, right? That you declare this static variable and then you immediately set it. You could declare that static variable and then initialize it here, right? Oops. All right, I'll just leave it like that. But otherwise, it's a cool tool used sparingly. Don't get carried away, right? All right, will it work? Let's find out. 5.3 or 5.7.3.1 blah 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 blah. What is? Well, I said 5.7.3, right? All right, is that the same number there? Looks like it to me. I can't paste into the console here, but it looks like it. All right, let's get crazy. 1,000. If I were to do this without memoization, without caching, we're not talking about 11,000 years anymore. We're talking about the heat death of the known universe, right? Billions, trillions, trillions, and trillions of years in the future. But I can do it in a matter of seconds if I'm smart about it. Let's see. Wolfram Alpha, can you do that? 1,000 first Fibonacci. In fact, Fibonacci. At this point, I probably have to go 1,001, like something like this. 70330, 70330. Excellent. I don't know how many digits are there, right, but there's a lot. 10,000? You can even do that. Probably not in the blink of an eye anymore. Oh, darn. So now I've hit now I have hit the limit of recursion here. Even though I'm using memoization here, I've gone 10,000 function calls deep, and apparently that's the limit of Java. I don't know. We could find out how many function calls I could make here. Can I make 5,000 function calls? Yep. Can I make 7,000 function calls? Nope. So how could I zero in on this? 6,000 function calls. All right, I can. So 6,500 function calls. All right, that's too much. What's next one I should try? I know that 6,000 is okay. I know that 6,500 is not okay. So somewhere in between, exactly in between, right? I'm zeroing in on this. So now where would I go? I know that 6,250 is okay, but I know that 6,500 is not okay. So in the middle, right? This is a preview of binary search that we're going to be looking at next week. Okay? But anyway, that was just a fancy there, I guess. Right? Finding out what we could do. 6250. Let's make sure it works, I guess. 66568. Oh, sorry, I'm off by one, remember? 1077095 blah 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 blah. So lots and lots of digits. So there is another solution that uses what's called dynamic programming. In this case, though, the dynamic programming, what does it become? This thing right here. So if you ever really need to compute Fibonacci numbers for some reason, then iterative is definitely the way to go. Any questions? Yeah.
Consider cheating if you use computer science to do your math homework?
Absolutely not. I don't think it's, no. My opinion is not the one that matters. So the question was, can you use computer science, in other words, programming, to do your math homework for you? I'll tell you a story. It was a coding theory course that I took. It's not coding as in like coding computer code. It's coding theory as in like Shannon entropy and information theory, where you can add redundant information to a code in order to send it over a noisy network and detect or correct errors on the other end, stuff like that. Anyway, they had us doing polynomial long division, and you can take one polynomial and divide another polynomial by it, right? But you have to do it, with a long division, so that you have to have a factor. Okay, here's a factor, and then subtract that off. Here's the remainder. Here's another factor. Do that, and you had to show all your work. Well, I found out that there was a LaTeX package for this. And so I just typed it up in LaTeX and let it generate the long division for me. And there's my work. I showed it. And, they were none the wiser. They thought I actually wrote out all that LaTeX. Or another example, you might not have taken it yet, but you will eventually, linear algebra and Gaussian elimination. So taking a matrix and finding the inverse of that matrix, or taking a matrix and multiplying another matrix together, right? Something like that. Gaussian elimination to solve a linear system of equations. Math folks will only assign systems of at most three variables, because you have to do all this work. Well, guess what I did? I just programmed it up, and I even programmed it to spit out LaTeX code so that it would do step-by-step process. And here you go. It ain't cheating if you program it. But that's just my take. If they want to see handwritten, then that's a different story, I guess. I mean, you can still write the program to have it dump everything out and then just copy it by hand. Right? There's nothing to prevent you from doing that. Okay. So for the rest of the semester, from now up until the break, we will be covering searching and sorting algorithms and searching and sorting code. It will probably only take us 2 weeks. So if you'll take a look at your schedule, we do have that Tuesday of the Thanksgiving week. So how many folks are jazzed about coming in on that Tuesday when you've got the next 3 days off? No? No takers at all? All right, fine. If we need to, I could still, broadcast from home if you want to see some exercises or something like that. But otherwise, 2 weeks for searching and sorting. We can go ahead and call it during that break week, and then when we come back, it's just the juice, right? The added extra topics, graphical user interfaces, and databases. Databases will only skim the surface of, because that's going to be a major topic in computer science too if you're continuing, right? Most of you are, I believe. Right? All right. We sometimes get non-majors taking the honors course as well. So that's the rest of our semester. There will be, how many more hacks do we have? 11, 12, 13, 14. 14 will actually lead into your project, and then you also have your final exam. No questions? All right, then I will see you next week, and have a good weekend.